Welcome back. Let's consider pressure volume loops for the ventricles. These are an extraordinarily useful way to understand the concepts that we first introduced in one of the previous videos. So, what do pressure volume loops have to tell us about the cardiac cycle? Well, consider this diagram. This image captures the left heart at the very moment that isovolumetric relaxation of the ventricle is ending, and the ventricle is just about to enter isotonic relaxation. The pressure in the left atrium of the left ventricle is 6, and it has an end systolic volume containing about 30 mL of blood. The left atrial pressure of 6 is the same as the left ventricular cavity pressure, and the mitral valve remains closed. Now, the left atrium has received some more blood, and so the left atrial pressure has risen to 7 millimeters of mercury, and this is greater than the pressure of 6 in the left ventricle, and so the mitral valve quickly opens. It only requires a very small differential in pressure for a healthy mitral valve to open briskly. Blood leaves the left atrium and enters the left ventricle. This is the very beginning of isotonic relaxation of the left ventricle. So the left ventricular filling commences, and the volume in the left ventricle must rise, and the volume in the left atrium must decrease. Initial filling of the ventricle is rapid, and this is called the phase of rapid passive filling, RPF. And here we are seeing the ventricular volume has reached 60 ml. But as yet, there has been little change in left atrial or left ventricular pressure, because at these low volumes, the left ventricle is very compliant. Left ventricular filling is beginning to slow down now, and this is called diastasis. As the phase of rapid passive filling starts to slow down, eventually movement of blood from the left atrium to the left ventricle actually stops briefly, and this phase is called diastasis. This is the phase after rapid passive filling, and the left ventricle is nearing maximum volume. The left atrium continues to empty, and so continues to fill the left ventricle. The left ventricular cavity is more than half full. The pressures are rising. We've reached 7 millimeters of mercury, as the ventricle is reaching about 70 mL of volume. As the ventricle approaches its maximum volume, the pressures rise higher, because at higher volumes, the ventricle is reaching the limits of its compliance. Essentially, its walls are less compliant or stiffer, so further filling is going to require energy to force more blood in, and this will be provided by left atrial contraction. Here we see atrial contraction, and the left ventricular cavity fills to 80 mL, and this generates a pressure of about 8 millimeters of mercury. This is the moment immediately before the onset of systole, and atrial contraction occurs. This occurs in the last 10% of diastole, a phase called protosystole. The left atrium contracts, increasing left atrial pressure dramatically and driving blood into the left ventricle. At this point, the left ventricular volume is about 90 mL, and the pressure in both the atrium and the ventricle is about 9 millimeters of mercury. This is the rapid active phase of ventricular filling. It is due to atrial contraction, hence the term active. By the end of atrial contraction, the left ventricle has reached its normal end diastolic volume of 100 mL, and the end diastolic cavity pressure has reached 12 millimeters of mercury. And by design, this pressure exists in the left ventricular cavity very transiently. But let's stop and look back at what has happened to ventricular pressures during the phase of isotonic relaxation. They started at about 6 millimeters of mercury and have risen to 12 millimeters of mercury with the delivery of 70 mL of blood, to combine with the already present 30 mL of end systolic volume to give a left ventricular end diastolic volume of 100. Now, ventricular electrical depolarization causes the onset of isovolumetric contraction, which increases the ventricular wall tension, and this is represented in the diagram here. This causes increasing cavity pressures and a rapid closure of the mitral valve, which generates the mitral component of the first heart sound. The pressure in the left ventricle is high enough to close the mitral valve, but not high enough to open the aortic valve, so at this point we have isovolumetric contraction. So the left ventricle, again, is essentially a spherical bag of muscle contracting on an incompressible liquid. It is mostly water, so it is incompressible. The left ventricular cavity pressure has now risen rapidly to 21 millimeters of mercury. The pressure must rise incredibly rapidly because blood is incompressible, and we are still in isovolumetric contraction, and the pressure now reaches 41 millimeters of mercury, now 61 millimeters, now 79 millimeters of mercury. But throughout this entire sequence, the volume of the ventricle has not changed. It is still 100 mLs. And we see that the aortic diastolic pressure is 80 millimeters of mercury. The left ventricular pressure is 79, so the aortic valve remains closed. Now, left ventricular pressure has hit 80 millimeters of mercury, and we are at the very moment just before left ventricular ejection commences. Now, in this image, left ventricular pressure has reached 81 millimeters of mercury, and the healthy aortic valve opens. Rapid ejection of blood commences, with of course a concomitant decrease in volume of the left ventricular cavity, but because the aortic root is full of blood, the systolic pressure continues to rise. Because the aortic valve is wide open, the left ventricle and the proximal arterial system becomes a single common chamber, and this almost instantaneously pressurizes the entire arterial system to a pressure of 99. The pressure in the left ventricle and the proximal arteries continues to increase, hitting 109 millimeters of mercury, then the ventricle, and by this time, the ventricle has emptied significantly. The reason the systolic pressure continues to increase is that blood is leaving the left ventricle and entering the large proximal arteries much faster than it is leaving the arterial system through the high resistance arterioles to enter the capillary beds. The pressure in the left ventricle and the proximal arteries continues to rise, and when the rate of blood entering the arteries is equal to the rate of blood leaving them, the pressure rises no further and it reaches its peak. In this case, it has peaked at 120 millimeters of mercury. After opening of the aortic valve, we see a phase of rapid ejection of blood, followed by the next phase, which is slower ejection of blood. In this slide, the pressure has started to fall from 120 millimeters of mercury to 110 millimeters of mercury, but we're still in systole. So what's going on here? Why is the pressure going down when the ventricle is still contracting? Well, the answer is that the blood is now leaving the arterial system and entering the capillary beds faster than the small amount of blood that is leaving the left ventricle and entering the arterial system. So, as ejection of blood from the left ventricular cavity slows down and the proximal arteries continue to empty, pressure in the single common chamber is going down, even though the left ventricle is still contracting. When the left ventricle reaches its end systolic volume, which is about 30 mLs, and at a pressure of approximately 80 millimeters of mercury, the aortic valve will close, and this happens because the left ventricle has cycled into relaxation, and so left ventricular cavity pressure must drop. And so if there's a pressure of 80 millimeters of mercury in the aortic root and the left ventricular cavity pressure has suddenly dropped a lot lower, then the aortic valve will close. This commences isometric relaxation, when the left ventricular cavity pressure decreases to 80, but the pressure in the aortic root is 81, then blood in the proximal aorta actually moves retrogradely towards the left ventricular cavity, and the healthy aortic valve cusps will immediately catch it, and the valve will snap shut. At this point, the ventricle is still at its left ventricular end systolic volume. So this is the phase of isometric relaxation. And when we see left ventricular cavity pressures plummet rapidly to 66, then 46, then 26 millimeters of mercury, all the way down to 6 millimeters of mercury with absolutely no change in ventricular volume, which is the end systolic volume, it is clear that this phase of relaxation must be described as isovolumetric or isometric. In this slide, we are back to where we started, with a ventricular pressure of 6 millimeters of mercury and a ventricular volume of 30 mils of blood. Pressure in the left atrium is only 6, so the mitral valve has not yet opened. Here, the left ventricular pressure is 6, the arrival of more blood into the left atrium is 7, and so the mitral valve will open promptly. At this point, The left ventricle is relaxing and its pressures will be going down, while venous return to the left atrium increases and its pressures will be going up. So the moment a 1 millimeter mercury gradient exists across the mitral valve, it will open. Blood starts to enter the left ventricular cavity. So isovolumetric relaxation has ended and isotonic relaxation has begun. So in this video, we have attempted to couple the changes in volume with the changes in pressure in the ventricles during a normal cardiac cycle. Let's talk about basic physics for the cardiovascular system. Let's cover a few very basic principles of physics first. Mass is a constant, but weight is not. Weight is the product of mass and the acceleration due to gravity, g. So weight equals mass times g. Once again, mass is constant, but weight is variable, because the acceleration due to gravity, g, is variable at different parts of the Earth's surface. So all mass is the same anywhere on the planet, but weight at the equator is greater than it is at the North and South poles. And that is because the Earth is not spherical, it is ellipsoid. So there is more of Earth's mass pulling you down towards the center of the Earth at the equator than at the poles. Momentum is the product of a body's mass times its velocity, and force is the product of mass times its acceleration. Remember that acceleration is rate of change of velocity. Tension is the force between 2 points. That is, this is linear tension, the tension along a straight line, and it equals force divided by length. Pressure equals the force acting over a two-dimensional surface area. So pressure equals force over area. The potential energy in a body of fluid is the energy it contains by virtue of its position in a gravitational field. And I find it useful to conceptualize potential energy of a fluid enclosed in any space as its energy density. Now, potential energy of fluid in a vertical cylinder equals its mass times its acceleration due to gravity times the height of the vertical column. It does not matter whether the vertical column is wide or narrow, whether it's at 90 degrees to the Earth's surface or if it's inclined. The vertical height will always be constant, and this is the basis of the water manometer. So, for a hydrostatic column of fluid, its potential energy is the product of its weight and its height. Kinetic energy is half the mass times the square of the velocity. Now, please remember this. It's very relevant to the cardiovascular system. In any hydraulic system, total energy equals the sum of the kinetic energy and the potential energy. In the cardiovascular system, there are rapid interconversions between kinetic energy, that is, energy due to blood flow velocity, and its potential energy, that is, its hydrostatic pressure. But the total energy of the system remains approximately the same. I say approximately because we're dealing with a real-life situation here in the cardiovascular system. There will be some losses due to the generation of heat. If kinetic energy increases, potential energy must decrease, and vice versa. In any closed system, such as the cardiovascular system, the law of conservation of energy always applies. Total energy must remain constant. Let us now talk about the tension in the wall of a hollow viscus, which can be a cylinder, like a blood vessel, or approximately a spherical or ellipsoid shape, like the left ventricle. The tension in the wall of the viscus is the product of the pressure times the radius divided by the thickness of the wall. Now, with reference to this diagram, let's assume that the thickness of the wall of the balloon is minimal. So, tension in the wall is the product of the pressure times the radius. Therefore, pressure will equal the ratio of tension over the radius. So in this image, the pressure in W, that is the wide region of the balloon, is the same as the pressure at N, which is the narrow region of the balloon, and so the pressures must be the same at all locations within the balloon. And this means that the pressures are equal. If the pressures in the wide and narrow sections are the same, then the ratio of tension over the radius for the wide section must be exactly the same as the ratio of tension over the radius for the narrow section. So tension 1 over radius 1 must equal tension 2 over radius 2. So for the wide section, the radius is large and the tension is high, and in the narrow section, the radius is small and the tension in the wall of the narrow section must be proportionately smaller than it is in the wide section. Okay, now let's move on. Let's consider the Bernoulli principle and the Venturi effect. Look at this diagram of a fluid passing from a wide vessel through a narrow constriction which opens out into another wide area of the vessel. When the fluid flows through the constriction, the velocity of the fluid will increase. As the forward velocity of the gas increases, its internal pressure decreases, and this is called the Venturi effect. As the forward velocity of a gas increases, the Venturi effect produces a decrease in its lateral pressure. And recognizing this, we have the Bernoulli principle. In fact, measurement of decreases in lateral pressure is one of the most incredibly accurate ways available to us to measure forward velocity of any jet. Now, the decreasing lateral pressure has the effect of entraining surrounding gas into the forward jet. A little machine that we used during anesthesia and surgery on the trachea is called the Sanders injector, and this makes use of the Venturi effect to provide positive pressure ventilation of the lungs with a high-speed jet of 100% oxygen without use of an endotracheal tube. The total volume of the oxygen jet delivered is relatively small, but a large volume of surrounding air is entrained by the Bernoulli principle, and a reasonable tidal volume can be generated. But with this arrangement, it is in fact impossible to measure the delivered tidal volume, or the pressures in the distal alveoli, or the inspired fraction or concentration of oxygen. Okay, let's move on again. Let's consider shear force between two layers in a blood vessel. First, we need to understand that cohesion is a force of attraction between two similar molecules of the same substance. Adhesion is a force of attraction between two different molecules. Look at this test tube. The water molecules exhibit cohesion with each other. The molecules of glass and water, such as occurs at the meniscus, where the glass and water molecules make an interface, these exhibit adhesion. If we have a piece of wood floating on a layer of water, there is a force between the molecules of water and the molecules of wood, and they exhibit adhesion. Now, a small force is applied to the wood. If the force of adhesion is greater than the applied force, the wood will not move, due to these forces of adhesion giving it inertia. When a larger force is applied to the wood, and the applied force is greater than the forces of adhesion, it can overcome the inertia, and the wood moves in the direction of action of the force. And this produces not only an acceleration in the wood, but a shear effect at the wood-water boundary. The applied force is called the shear force. Just as shear forces can separate adjacent layers of wood and water, the same effect can separate layers in the wall of a blood vessel. And this is termed dissection. The ingress of high-pressure arterial blood through a rip in the endothelium between the layers of tissue in the wall of a vessel like the aorta is called a dissection. And these layers can separate. It gives rise to a flap. And under the flap is an expanding space as it fills with blood called a false lumen. The false lumen can expand and encroach on the capacity of the true lumen. This is the appearance on an echocardiogram upon which the diagnosis of aortic dissection is made. One special area of general physics is hydraulics, and this deals with laminar and turbulent flow and the Reynolds number, and we will discuss this in a later presentation. So, thank you for listening to this very brief presentation on most of the basic physics you will need to understand the cardiovascular system.